Welcome back. Today, we're dissecting multi-region architecture. This is a highly tested exercise in constrained optimization. We are dealing with immense physical scale. Cloud providers operate dozens of regions across continents, linked by fiber optic cables spanning oceans. The physical distance between these data centers dictates everything. Designing for this scale requires a ruthless filtering process. You are never maximizing a single variable like speed or carbon efficiency. You are balancing competing demands to find a solution that survives reality. This flowchart shows the 5-step decision framework. Notice how each factor must be weighed. We begin with absolute constraints, data residency laws, and the physical latency dictated by the speed of light. Carbon intensity acts as the final tiebreaker, not the starting point. If you prioritize these factors out of order, especially placing carbon first, you guarantee an architecture that will fail legally, technically, or financially. This brings us to a common exam topic: architectural anti-patterns. The most dangerous trap you will see is carbon-only region selection. It is very tempting to choose the cleanest possible region, like a facility running on 100% hydroelectric power. But doing so often creates massive physical distance between the servers and the actual users. Routing traffic across continents means every router and switch consumes power, destroying any localized carbon savings. Shifting the facility closer to the user reduces the network path. Total system energy drops, and the application responds quickly enough to be usable. You will also see 3 other common traps: premature multi-region deployment, which adds standby costs before there is a clear requirement; symmetric capacity, which wastes servers by provisioning 100% idle capacity for regions serving only 10% of traffic; and region proliferation, where additional regions are spun up but never retired. Sustainability in IT architecture is a system-wide calculation. An isolated green data center is counterproductive if it forces your data to travel halfway across the globe. Let's apply this framework to a complex exam scenario. Consider a government healthcare system governed by strict data residency laws. The system requires 2 independent regions to meet its high availability targets. However, there is only one legally permitted cloud region inside the country's borders. You solve this by splitting the architecture by legal classification. We keep the highly regulated patient-identifying information locked tightly within the domestic region. Then, we move the application servers and the de-identified data across the border into a secondary foreign region. This specific split satisfies the regulatory constraint by keeping sensitive records domestic while fulfilling the redundancy requirement by allowing the application layer to span globally. Elite architects slice monolithic systems into discrete legal components to satisfy the competing demands of both law and physics. Once you deploy across multiple regions, you face the next mechanical challenge: keeping data identical in all locations. This introduces the trade-off between synchronous and asynchronous replication. This chart illustrates synchronous replication on the left. Think of it like a group text message where you have to wait for every single person to reply before you can send the next text. Notice the multiple coordination round trips. A write operation is not acknowledged to the client until every replica confirms it has stored the data. This requires high write energy and significant time, but it guarantees perfect consistency. Now compare that to the write timeline showing asynchronous replication. This is more like posting a message in a group chat and immediately moving on. The primary database acknowledges the client as soon as it stores the write locally, and the replicas catch up in the background. It saves energy and lowers write latency, but you risk brief periods where the replicas hold stale data. Examiners test your understanding of this exact trade-off using a highly specific user symptom. A user updates their profile, hits refresh, and momentarily sees their old information still displayed on the screen. This is the classic read-after-write anomaly caused by asynchronous replication lag. The user's read request landed on a replica that hadn't caught up to the primary yet. If the exam asks to solve slow cross-region reads, the answer is to add a local read replica, not tear down the multi-region deployment. Data consistency is strictly bounded by the speed of light. You have to consciously trade either speed or absolute accuracy based entirely on what the application needs to do. Beyond data replication, there is an invisible energy drain in cross-region architectures. The initial handshake required every time a database connection is opened. If an application opens and closes a connection for every single request across regions, it wastes massive amounts of processing time just negotiating those connections. Each request travels across continents, hitting a destination to establish a new connection protocol before any payload data transfers. Connection pooling fixes this. By reusing long-lived permanent pipes between regions, data instantly bypasses the handshake barrier. Bypassing that cross-continent setup saves tens to hundreds of milliseconds per request. Over millions of queries, this dramatically reduces the server's resource consumption and compounds your energy savings. This brings us to a macro strategy for the exam. When faced with multiple choice questions balancing these complex factors, you need to identify the trick options. The trap is the extreme answer. You will see options offering the absolute lowest latency, or the cleanest grid, or the absolute cheapest cost. In architecture, extreme answers containing the word always, or prioritizing a single variable at the expense of the others, are traps. The correct choice is usually the balanced option that satisfies all constraints moderately well. Mastering multi-region architecture is entirely about managing compounding effects, whether you are eliminating the compounding latency from network handshakes or avoiding the compounding errors of extreme design choices. To build sustainable, highly available systems, you must filter your choices sequentially, by law, by physics, by budget, and finally, by carbon. You've just conquered one of the hardest topics in the course, multi-region architecture, with all its swap traps. Next, database and caching architecture. We'll master polyglot persistence, the 4 write strategies, and the cache hit rate that determines whether your cache actually saves energy. You're doing amazing.